Every day, 40 tons of green coffee are stripped of caffeine deep inside a Canadian facility using pressure so intense it would crush a submarine. This operation exists to create decaf that claims to match the flavor of the original bean. The official narrative promises pure coffee without chemical residue, and massive demand hinges on that claim. But beneath the reassuring labels are skyscraper-sized autoclaves, relentless energy costs, and extraction methods that reshape everything from bean chemistry to the global beverage market. If decaf is just coffee without the stimulant, why does its production require an industrial feat on par with oil refining? And what does that really mean for your morning cup? The answers begin where the process looks most high-tech and convincing, at the threshold of the Swiss water plant supercritical carbon dioxide extraction line. Inside the Swiss water facility, the numbers that drive decaf production become tangible. One extraction line alone handles up to 40 tons of green coffee beans every day, a volume that would fill a city bus every hour. The heart of the operation is a supercritical carbon dioxide autoclave, a vertical steel column 2 to 3 meters in diameter and about 20 meters tall. This vessel towers over the production floor, built to withstand pressures of 250 to 300 bar, about 300 times atmospheric pressure, and temperatures between 65 and 80 degrees Celsius. The walls are thick, the valves industrial grade, and every seam is monitored by a web of sensors feeding data to a glassed-in control room nearby. Here, a carbon dioxide process engineer stands at the interface between raw green coffee and the invisible force that will strip away caffeine. The extraction cycle is relentless. Supercritical carbon dioxide, compressed until it behaves like both a gas and a liquid, is pumped through the autoclave at a rate of 140 cubic meters per hour. That's enough to fill a large swimming pool every morning, circulating through tightly packed columns of beans for nearly 24 hours straight. The system is designed for consistency. Beans enter at a set moisture content, are loaded in steel baskets, and sealed inside the column while pressure ramps up. The entire process is controlled from a digital dashboard, where every variable, pressure, temperature, and carbon dioxide flow is tracked and logged in real time. This scale does not just exist for show. Each autoclave run can decaffeinate up to 8 tons of coffee at once, and several columns operate in parallel to meet demand. The plant's daily throughput is only possible because every step is engineered for continuous operation. While one column is charging with fresh beans, another is in the extraction phase, and a third is being depressurized and emptied. The entire line runs on a schedule measured in minutes, not hours, with operators coordinating shifts to keep coffee moving from intake to finished decaf. Maintenance teams inspect gaskets and pressure relief valves between cycles, aware that even a brief interruption can cascade into delays across the plant. The numbers behind this system are staggering. In a single day, the plant will process enough beans to supply millions of cups of coffee, each batch logged by origin, time, and extraction parameters. The control room is lined with displays showing live data from every autoclave, alerting operators to even the slightest deviation. It is here that the abstract idea of decaf production becomes a matter of physical reality, measured in tons, bars, degrees, and cubic meters per hour. Before the chemistry of caffeine removal can be explained, the sheer industrial presence of the process is impossible to ignore. Supercritical carbon dioxide is neither a typical gas nor a typical liquid. When carbon dioxide is compressed to pressures above 250 bar and heated to from 65 to 80 degrees Celsius, it enters a state where its density rivals that of a liquid, but it flows and diffuses like a gas. In this form, carbon dioxide becomes a highly selective solvent, able to slip through the microscopic pores of coffee beans and dissolve caffeine molecules with remarkable precision, while leaving behind the vast majority of flavor compounds. This selective power is rooted in physics. Caffeine, a small and relatively nonpolar molecule, dissolves readily in supercritical carbon dioxide, especially under these high-pressure and moderate temperature conditions. Larger, more complex flavor molecules responsible for the aroma, acidity, and body of coffee are far less soluble in carbon dioxide. They remain locked inside the cell walls, protected by their size, shape, and chemical structure. As supercritical carbon dioxide courses through the packed bed of beans, it acts as a molecular sieve, stripping out caffeine while sparing the delicate solubles that define each coffee's origin. Extraction efficiency is a function of both time and flow rate. With a throughput of 140 cubic meters of supercritical carbon dioxide per hour, the system achieves 97% or more caffeine removal in a single 24-hour cycle. The process is fine-tuned to maximize mass transfer. Carbon dioxide penetrates deeply into swollen beans, dissolves caffeine, and exits carrying the target molecules. Pressure and temperature are held within tight tolerances, ensuring that the solvent's density and viscosity stay in the optimal range for caffeine uptake without leaching away key flavor precursors. One of the main advantages of this method is its clean finish. Supercritical carbon dioxide is an inert food-safe compound that leaves virtually no residue behind. After extraction, the system is depressurized, carbon dioxide returns to a gaseous state, and any trace amounts simply dissipate. No chemical solvents, no lingering aftertaste, just decaffeinated beans that retain their original sensory profile. This residue-free promise is a major reason why carbon dioxide decaf is favored for specialty and organic coffees. Yet the underlying physics comes with a hidden cost. For carbon dioxide to work efficiently, the beans must be prepared in advance, swollen with steam to open up their cell structure and allow the solvent to reach every pocket of caffeine. This pre-steaming step and the drying that follows are among the most resource-intensive phases in the entire process. The science of supercritical extraction delivers purity and selectivity, but every advantage carries its own demands on water, heat, and time. Steam surges through insulated pipes, feeding into chambers where green coffee beans wait to be transformed. The pre-steaming phase is both routine and relentless, and it is here that the plant's true appetite for water and energy comes into focus. Every ton of beans absorbs an extra 20 to 32 kilograms of water during this step, pushing their moisture content up to about 12 to 14%, just enough to open the cell walls and maximize caffeine extraction. With a daily intake of 40 tons, the numbers add up quickly. Hundreds of kilograms of water are cycled into the beans before decaffeination even begins. The energy behind this process is measured in heat and pressure, not just numbers on a dashboard. Boilers fire constantly to deliver steam at 120 to 135 degrees Celsius, operating at 2 to 2.5 bar. For each ton of coffee, generating that steam demands between 2.2 and 2.7 gigajoules, enough to power a typical North American home for nearly a month. After extraction, the beans must be dried back down to 10 or 11% moisture, which means running industrial dryers for 4 to 8 hours per batch at temperatures up to 105 degrees Celsius. Evaporating that absorbed water requires another 45 to 70 megajoules per ton, a process that is repeated dozens of times a day across multiple lines. At the center of these operations stands the plant's operations and sustainability manager, tracking every cubic meter of water and every kilowatt hour. Boiler logs, heat recovery schematics, and energy meters are reviewed in real time, searching for ways to capture waste heat or optimize the cycle. Even with efficiency upgrades, condensate return and exhaust to feed water exchangers, steaming and drying together account for nearly 2/3 of the plant's total energy footprint. The push for greener decaf is not just about the absence of solvents. It is a daily negotiation with the physics of water, heat, and time. Chemical decaffeination often relies on two main solvents, methylene chloride and ethyl acetate. Each solvent shapes the flavor, the safety profile, and the regulatory scrutiny of the final cup. In the methylene chloride process, green coffee beans are first moistened with steam until they reach about 16 to 18% moisture. This swelling opens the cell walls and prepares the beans for extraction. Next, the beans are soaked in methylene chloride at about 105 degrees Fahrenheit. The solvent selectively dissolves caffeine while leaving most of the other flavor compounds behind. Once the caffeine is removed, the beans go through a rigorous steaming phase at 210 to 220 degrees Fahrenheit for 1 to 2 hours. This step is critical. It strips away any remaining traces of methylene chloride and drives residues down to levels well below the limit set by the FDA of 10 parts per million. Routine lab testing, often using gas chromatography, confirms that most batches fall far below that threshold, sometimes under 2 parts per million. If a batch ever exceeds the limit, it is re-steamed and retested before release. Ethyl acetate offers an alternative approach, and it is often marketed as a more natural solution. Ethyl acetate can be synthesized or derived from sugarcane molasses, which is why it is sometimes called the sugarcane process. The workflow is similar. Beans are steamed, then rinsed in closed-loop systems with ethyl acetate to dissolve the caffeine. After repeated cycles, the beans are steamed again and then roasted, which helps drive off any residual solvent. Unlike methylene chloride, there is no universal legal limit for ethyl acetate residues in decaffeinated coffee. Industry practice and routine lab checks ensure that levels are typically undetectable in the finished product, however. Producers rely on process control, steaming, and roasting to reduce residues to negligible levels. Sensory outcomes differ as well. Methylene chloride decafs are known for a clean, muted flavor profile, while ethyl acetate decafs often retain a brighter, fruitier character. That brightness is linked to the ester chemistry of ethyl acetate. Both methods demand careful process control, but the regulatory landscape sets a firm boundary for methylene chloride, while ethyl acetate's natural reputation and lack of a fixed residue limit leave more room for interpretation. The contrast between these chemical routes and solvent-free processes sharpens the debate over what matters most in decaf coffee: trace residues, process transparency, or the final taste in the cup. Whatever the chosen route, rigorous testing and careful steaming remain essential to deliver safe, flavorful decaf coffee to consumers. The Swiss water process takes a radically different approach to decaffeination, one that relies on equilibrium chemistry rather than chemical solvents or supercritical gases. At its core is green coffee extract, called GCE, a solution saturated with coffee solubles but stripped of caffeine. The process begins by soaking an initial batch of green beans in hot water, drawing out not just caffeine, but also the full spectrum of flavor compounds. Caffeine is then selectively removed from this extract using activated carbon beds, leaving behind a liquid that mirrors the composition of coffee minus the stimulant. This caffeine-free GCE then becomes the working solvent for all later decaffeination cycles. Fresh batches of green beans, pre-soaked to reach the right moisture content, are immersed in circulating GCE. Over the course of 8 to 10 hours, caffeine migrates out of the beans into the extract, driven by the concentration gradient. Because the GCE is already saturated with flavor compounds, only caffeine is pulled from the beans, while aroma, acids, and sugars remain largely intact. Lab technicians monitor total dissolved solids, pH, and caffeine concentration to ensure the extract stays in balance and does not begin to leach flavor from the beans. Maintaining this closed-loop system requires significant resources. On average, about 56 kilograms of water are cycled for every kilogram of coffee processed, a figure that far exceeds the water use of solvent-based methods. Activated carbon beds capture caffeine from the GCE, and these beds are regenerated regularly with hot water or steam, consuming additional energy. Wastewater from the process, rich in organic compounds, is treated on site before discharge, with up to 85% of water eventually returned to the local supply. The Swiss water process stands out for its absence of chemical residues and for preserving the natural flavor of the bean. That benefit comes with an environmental trade-off: high water use and the need for careful management of both carbon and wastewater streams. In the end, the chemistry helps preserve the essence of the bean, but not without a substantial investment in water and energy. Miguel R., the plant's head roaster, stands over a pair of roasting drums, weighing out two identical batches, one regular, one decaf. The differences start before the first bean hits the steel. Decaf beans arrive lighter, trimmed by 1 to 2% of their original mass after caffeine and water are removed. The beans themselves feel more brittle in the hand, their surface roughened by the swelling and drying cycles they have endured upstream. During roasting, these changes become impossible to ignore. Decaf beans are more prone to fracture, with chip and breakage rates climbing to 2 or even 4%, compared to less than 1% for untreated coffee. To compensate, Miguel drops the initial charge temperature by nearly 10 degrees Celsius, slowing the rate of heat transfer and reducing the risk of scorching. The roast curve stretches out and development time extends by a minute or two, allowing the beans to reach the same color and extraction yield as their caffeinated counterparts. Every adjustment is logged, from drum speed to airflow, as Miguel works to coax a balanced cup from beans that have already traveled through the gauntlet of decaffeination. The process is more than a technicality. It is a hands-on negotiation between chemistry and craft, shaping the flavor and body of every decaf batch before it ever reaches the cup. Caffeine, once stripped from the beans, does not go to waste. At the Swiss water plant, every 100 kilograms of green coffee yields about 1 kilogram of pure caffeine, collected, refined, and sold as a valuable commodity. This byproduct, tested to exceed 99% purity, finds its way into soft drinks, energy supplements, and pharmaceuticals. The revenue from these sales helps offset the high cost of decaffeination, turning what was once a waste stream into a line item on the balance sheet. Quality control underpins every batch that leaves the facility. The plant's quality assurance manager oversees a battery of tests, both in-line and in the lab, to verify that each lot meets strict standards. High-performance liquid chromatography and gas chromatography, mass spectrometry, are used to confirm that the final caffeine content remains below 0.10% and that any solvent residues, when present, are well within regulatory limits. If a batch falls outside specification, it is immediately flagged for rework and never released to the market. The lab's protocols are exacting, but the stakes are clear. Safety, compliance, and the reputation of the Swiss water name depend on getting it right every single time. Global decaf production relies on a surprisingly small network, just a few dozen large plants worldwide. When a high-pressure compressor fails or a boiler goes offline, shipments can back up in days, not weeks. In February 2022, a compressor outage at Swiss Water stretched lead times and sent spot premiums soaring by up to 40%. Supply chain managers track these events closely, knowing that a single bottleneck, whether in compressors, steam plants, or carbon adsorbers, can ripple across the entire market. To avoid costly surprises, buyers follow a strict checklist. They verify plant uptime records, request third-party batch certificates for caffeine and solvent residues, and confirm water and energy use disclosures. They also demand clear protocols for out-of-spec batches and transparency on caffeine byproduct sales, which can affect green bean pricing. In a market this concentrated, preparedness is the only safeguard against delays and price spikes. For anyone sourcing decaf at scale, vigilance is not optional, it is essential. Every cup of decaf now depends on a handful of global plants running at full tilt, each one balancing chemistry, energy, and ever stricter quality rules. As demand for caffeine-free options grows, the pressure to decaffeinate sustainably and transparently only intensifies. The next sip is not just about taste, it is about trust in the unseen science behind every bean.